Hi and welcome to Quick Add Maths on Quadratic Inequalities. The prerequisite to continuing this tutorial is that you would already have a good understanding of linear inequalities. For example, when 5 brackets of x minus 2 is larger than 25, this would lead to x being larger than 7. Also, when 25 minus 2x is less or equal to 17, this would lead to x being larger or equal to 4. With the help of the graph on the right hand side, when a quadratic function takes the form that has a minimum value that is less than 0, its graph will intersect with the x-axis at 2 points. Let's call this P and Q for now, where P is the larger of the two. In all such instances, the solution for the inequality representing the same notation would see to x being larger than P and x less than Q. The rationale based on what we've learned in our earlier videos is when the minimum value of ax squared plus bx plus c is less than 0, the symmetrical parabola will intersect the x-axis at 2 points. With the clear distinction that the larger of the two values is P, it is evident from the graph that its y value will be larger than 0 beyond the value of P. Likewise, the y value will be larger than 0 for when x is smaller than Q. For completeness, the solution for ax squared plus bx plus c being less than 0 is when x is in between Q and P. Next, I wish to take you through when its x squared component is negative. This is when fx is equal to a minus ax squared plus bx plus c, which should now have a maximum value that is more than 0. Here, you'll be able to solve for two values of x. Again, we'll represent it as p and q, where p is larger than q. In this case, the solution for ax squared plus bx plus c being larger than 0 is when x is in between q and p as shown on the graph. For completeness, the solution for when minus ax squared plus bx plus c is less than 0, it happens when x is larger than p and x also being smaller than q. To have a better grasp of the concept, let's move on to tutorial question 1, where we are asked to solve for the stated inequality. Knowing that the x squared component of the entire equation being a positive 2, this is a U-shaped parabola. In solving the equation, we know that the parabola cuts the x-axis at minus 0.5 and 6. From the given inequality, we are looking for the portion of the parabola when its y value is below the x-axis. This is going to be when x is strictly between minus 0.5 and 6. As an extension to the above, if the equation cannot be easily factorized, you could solve x by using the quadratic formula. Tutorial question 2. Solve for x that fulfills both inequalities. For such a question, you would independently solve inequality 1, then inequality 2, and work towards the required solution as a range that fulfills both inequalities. Let's do this again using a different set of inequalities for tutorial question 3. Again, in independently solving for inequality 1 and inequality 2, the required solution is the one that fulfills both inequalities. Moving on to tutorial question 4, where we will introduce modulus to the inequality. For the preliminary working, you must be able to apply what is learned from 2.3 to get to drawing the yellow curve as a representation of y equals modulus x squared minus 8x plus 6. Next, we go on to draw the blue line, which is a translation downwards by 6 against the yellow line, for it to represent the equation y equals modulus x squared minus 8x plus 6, and all this together subtracting by a further 6. We shall then go on to identify all the 4x values at which the blue line cuts the x-axis, then label them on the x-axis as per our calculation. The required solution warrants us to identify the domain at which the range of the given notation is negative. From the graph, this would be the values when x is in between 0 and 2, and when x is in between 6 and 8. That's all for quadratics. And if you've liked what you've seen, please be on the lookout for our other tutorials.